Hi, I'm Alistair Greener. Welcome to Special Chem Tutorials. Today we will be talking about how to select the best matrix material for use in your high temperature composites. The goal is to exploit the full performance of your composite in your particular application. This will let you develop new products for markets that use high temperature composites, like automotive and electronics. Previously, if you worked on this topic and did not achieve the desired performance from your high temperature composite, it is surely because the matrix polymer you used was not suitable for your high temperature application. In fact, many formulators are used to work with an epoxy matrix, and rather than starting from scratch with a new material they are unfamiliar with, they prefer to try twisting the epoxy matrix to adapt it to very high temperatures. But epoxy matrix is not suitable for very high temperature applications. We will explain why in this tutorial. Now let's see in detail what we will discuss in today's tutorial. First, we will show the current practices used for selecting matrix polymer in high temperature composites and discuss the issues associated with those approaches. Then you will be introduced to better materials and provided with a step-by-step explanation of how to choose the best one for your application. Finally, we will provide several practical examples of applications where very high temperature composites are required. Before we start, let me tell you a few words about the creator of this tutorial. Dr. Mark Demise holds both a MS and PhD in chemistry from Illinois Institute of Technology in Chicago, Illinois. He has more than 30 years of experience in both management and technical positions at several different plastics companies. His main area of expertise is in the development of structure-property processing relationships for polymer-based materials, including high-temperature composites. Currently, he runs his own consulting business and specializes in assisting organizations assess new technologies. He has published over 50 papers in various technical journals and holds 35 patents both US and worldwide. Now let's turn to matrix materials for high temperature composites. A picture of a typical composite structure is shown on this figure. The primary function of the matrix material in the composite is to hold the fibers together and protect them from mechanical and environmental damages. Currently, for high temperature composites, epoxies are the primary choice for a matrix material. Indeed, formulators are familiar with epoxies and are used to working with them as matrix materials. And on the other hand, they are unfamiliar with using many other materials. So they think it would be quicker to slightly modify epoxies to make them work at high temperatures rather than starting from scratch with a new material. This is the current general approach for selecting a matrix material. Now, let's look at the issue with this approach for high temperature composites. We are seeing an increasing need in new applications to formulate composites that can be used at very high temperatures, sometimes over 250 degrees centigrade. Also, in many of these new uses, the produced composite part needed is used at these very high temperatures for very long periods of time. You will face an issue when using epoxies as the matrix material in these high temperature composites. Indeed, their thermal stability is not sufficient. At the temperatures that we have been talking about, epoxies will begin to degrade. That will lead to the loss of properties. The loss in properties means that your high temperature composite will not have the performance that you expected. Thus, you will lose new markets and potential clients. Now let's look at the way to solve this problem. There are polymers other than epoxies that can be used as the matrix material in your high temperature composite. In general, we can break those polymers into two classes: thermosets and thermoplastics. Now let's take a closer look at each of those categories of materials. Let's start with thermosets that can be used as the matrix material in your high temperature composite. A general distinguishing feature of thermosets is that they begin as liquid resins that thermally cure to solids. Thermoset resins that can be used as the matrix material in your high temperature composite include polyimides, bismaleimides and cyanide esters. Now let's turn to the class of thermoplastics that can be used as the matrix material in your high temperature composite. Thermoplastics begin as a solid at room temperature and are processed in a melted or liquid state. Two thermoplastics that you can use as the matrix material in your high temperature composites are polyether imide and polyether ether ketone. Now let's turn to how we go about selecting the right matrix material for a high temperature composite. There are many factors that need to be considered when choosing the right matrix material. The three most important criteria are environmental resistance of the matrix, mechanical properties, and cost. For environmental resistance, we should be concerned with the operating temperature and exposure to sun, water, and chemicals. For mechanical properties, we should think about strength, stiffness, and toughness. In terms of cost, both the material and the production costs need to be considered. We also need to be aware of the mechanical properties of the matrix material as a function of temperature. Since your high temperature composite is used at temperatures above room temperature, its strength and stiffness at elevated temperatures are crucial parameters. A parameter you can use to characterize those parameters is the softening temperature of your matrix material. In amorphous materials like polyether imide, the softening temperature means the glass transition temperature. In matrix materials like polyether ether ketone, the softening temperature means the melting temperature of the matrix material. The matrix you choose should have a processing temperature at least 50 degrees Celsius higher than its service or use temperature. Making the choice of the right matrix material for your high temperature composite is further complicated. Indeed, the possible choices do not excel in every category. For example, one material might be inexpensive and have good corrosion resistance, but have a very low softening temperature. On the other hand, you might have another material that has a very high softening temperature, but is very expensive and has very poor hydrolytic and solvent resistance. No one polymer will have all the most desirable features without having some negative features as well. The solution to this problem is to know the most important feature of your high temperature composite in its desired application. One of the most important parameters in this regard is the desired temperature at which your product will be used. That parameter is the first criteria you should consider for the selection of your matrix material. For example, if the service temperature for your composite ranges between 135 and 250 degrees centigrade, the right matrix materials will be bismaleimides, cyanide esters, or aromatic thermoplastics. On the other hand, if your desired service temperature ranges between 250 and 350 degrees centigrade, the required matrix material is a polyimide with a high softening temperature. The key requirement is the retention of the properties at high temperatures with a reasonable trade-off among the other features. A secondary feature for the selection of the right matrix material for your high temperature composite is the particular production method that you are using. In comparing the general class of thermosets to thermoplastics, thermosets are generally easier to process due to their relatively lower viscosity. On the other hand, thermoplastics offer lengthy prepreg shelf life and possess exceptional impact resistance. In addition, they provide the opportunity to use recycled content in your high temperature composite. Now let's look at several examples of choosing the right matrix material in a high temperature composite. The first example that is focused on choosing the right matrix material in your high temperature composite is based on the needed surface temperature for your product. It involves an airplane part that experiences engine exhaust. There were two choices for the matrix material: epoxies and bismaleimides. The original part design used an epoxy as the matrix material in the composite. However, during routine operation of the airplane, an actual surface temperature of 200 degrees centigrade was determined based on the part's exposure to exhaust from the airplane engine. Therefore, the part design was switched to using bismaleimide as the matrix material. That decision was based on the fact that the bismaleimide provides the required use temperature and also processes very much like an epoxy. If the right matrix material had been used initially, much time and money could have been saved. The second example involves the use of polyimides as the matrix material in high temperature composites. Design goals for new commercial aircrafts have pushed sustained service temperatures to the range of at least 300 degrees centigrade. Epoxy-based composites can meet the requirements of about 125 degrees centigrade, but certainly not those very high temperatures. You need to find an alternative matrix material for this application. The surface temperature is directly related to the glass transition temperature or softening temperature of the matrix material in the composite. The table summarizes the glass transition temperature values of both epoxies and a high temperature polyimide. The designated polyimide can endure surface temperatures in carbon fiber composites as high as 335 degrees centigrade. Thus, it will satisfy the needs for the aircraft application. The matrix material has been specified based on its glass transition temperature, and you can use that approach in developing your own high temperature composites. Let's summarize what we have learned today. First, we have learned that epoxies are not the best matrix material for use in your high temperature composites. Even though they are familiar materials, their lack of high temperature stability limits their usefulness in that application. At the temperatures that are used for high temperature composites, epoxies degrade and lose their physical properties. That loss in properties means that your high temperature composite will not perform as expected. We have introduced alternatives to epoxies for use in your high temperature composites. Those alternatives satisfy the temperature requirements of new applications for high temperature composites like commercial aircraft. As such, their use will allow you to enter these new markets and attract new customers to your business. We have provided criteria for the selection of the matrix material in your high temperature composite. The most important feature of the composite is the surface temperature that the composite must withstand. That determines the softening temperature that the matrix material must possess to be used in your particular application. Finally, we have provided several examples of how to use the softening temperature as a selection tool for choosing your next matrix material. These examples provide epoxies as comparisons and explain why they are not suitable for use in the particular application that is discussed. Then, based on the introduction of the alternative matrix materials, a selection is made of the right material for use in your high temperature composite. You are now ready to choose your own matrix material for the development of new high temperature composites. I look for you to choose your matrix material based on the needed surface temperature and the softening temperature of the matrix material. With the things that you have learned today, you can develop exciting new high temperature composites for novel markets. That will allow you to attract new customers and work in new business areas. How did we do today? Please rate and comment this tutorial. It will help your colleagues and peers make up their mind about watching this tutorial too. See you soon for another special Chem tutorial.